Hello and welcome to Magnet Geological. In this video we will help you envision real estate through the eyes of a geologist. We are not brokers, agents, geotechnical engineers, or provide environmental services. We provide a brief, financial opportunity and risk-oriented intrinsic geological summary of your property, prospective property, collateralized property, or prospective collateralized property. And we provide geochemical testing on bedrocks, soils, and water. Geochemical testing offers real insights into land at a very reasonable cost. Our tests cover precious metals like gold and silver to heavy metals like chromium to lead. Also critical elements like rare earth elements and lithium, types of clay like expansive clays, agricultural tests like cation exchange capacity. Water tests include both inorganic and organic components. And we follow up with you and explain the results. In-depth evaluations and training programs are also available at your request. The principal of Magnet has used these methods profitably in his own business for over 40 years. We fully enjoy geology and strive to be of assistance to you.
Hello, my name is Bud Johnson. I am a Texas licensed geoscientist and principal at Magnet Geological. It has been said not understanding geology is like walking the halls of the Louvre with the paintings facing the walls. Geology is art, science, and history. But more importantly, geology is the foundation of our economy. It is the origin of the food you eat, the water you drink, your housing materials, the core of the energy you require, and it is the foundation that every other foundation is built upon. In this video, we will talk about the intrinsic values of real estate. You are likely more familiar with an appraisal of real estate. An appraisal yields a market value that will fluctuate with the economic times and might overlook some of the more esoteric elements of a property. What we mean by intrinsic is the sum of its natural or native components. On the upside, this might be a petroleum reservoir, a freshwater aquifer, or an accumulation of critical elements. On the downside, perhaps there is an unseen fracture pattern that is developing a new karst and sinkhole trend which could alter your development plans. We strive to provide useful information for due diligence in the form of a risked and discounted factor that you may choose to apply an appraisal or plan. That is there an unseen component that might affect the market value either up or down? And if so, what type of risk or opportunity is associated with the intrinsic components? 250 million years ago, had you been around, it would have been possible to have ridden a small bipedal dinosaur from the Stampede in Calgary through the Houston Rodeo into Rio de Janeiro, across Central Africa and to Sydney, Australia, where you would have encountered an Amazon-style river system with much sand and some kaolinite clay with iron-rich minerals. The sand, clay, and minerals form the workable Sydney sandstone that oxidizes to the nice earthy tones of Sydney buildings. Much later, the Parramatta River developed that ran through the Sydney location during the last glacial maximum. As the glaciers melted, sea levels rose and flooded the river valley, forming the harbor. And, as a consequence, the rising sea level enhanced the Great Barrier Reef to the north. The original ships to Australia preferred the easy harbor of Sydney to the chance of being shipwrecked on the Great Barrier Reef. This combination of geological events and consequences formed the foundation that is now Sydney, Australia. Today, Sydney's economy is dominated by finance, insurance, and mining, both locally and as headquarters for many Asia-Pacific multinational corporations. Tourism and agriculture are also major economic components that have sprouted and grown from this excellent geologic foundation. Next, Allison will talk you through some geological insights into Boston and New York real estate. Then we will look at some basics in agriculture, mining, and petroleum. We are here to assist. If you have questions or need assistance, please find us at magnetgeological.com and send us an email.
Thanks, Bud. Boston has a uniquely shaped city center. Property values are likely to share this peculiarity. We can look at the geological reasons for this both in Boston and later in Manhattan. As Bud mentioned in the previous segment, 250 million years ago, you could have traveled from North America to Australia, including crossing Africa. In this interval of time, we formed a supercontinent called Pangaea that included Africa juxtaposed to North America. In a highly complicated fashion, as they approached each other, they first formed the Appalachian Mountains. Later, as they parted, faulted rift basins formed and the beginning of Boston Harbor. These basins were infilled with detrital material, mostly sands and gravels. Much later, after North America and Africa are far apart, comes the Ice Ages. Sea level was much lower and river systems are developing into a lower sea level system. Then we have the approach of the glacier, which is followed by the retreat of the ice sheets. Both approach and retreat have an effect on the land. In general, glacial material is referred to as till. Till detrital is typically a wide assortment of highly compacted, but unstratified material from clay to boulder sized that can usually be used for major foundations. As the glacier retreat, sea level rises. Some of the geologic features formed might be covered in water, or it might be said that they were drowned. Some of the features are left as topographic highs, perhaps islands or peninsulas. The origin of Boston is about 1630. The topography would have been very different at the time. There was considerably more harbor, and less Boston, less land. Of course, Boston is associated with much early American history, including political and economic activity. With this came people that needed food. An old idea from Europe was brought with them called a tidal mill. This is a development or processing system to convert grain, such as wheat, into flour for the production of bread. They used the natural rise and fall of the tide to drive the mill. High tide was captured in man-made tidal ponds, then released slowly during low tide to drive the mill to grind the grain to flour. Ultimately, the mills were moved inland and upstream to elevated locations to run the mills on rivers. These large tidal ponds located in Boston Harbor were then infilled to provide more land for a growing Boston. Essentially, these are man-made mud flats. Even though the material was likely of good quality, it has not had the time to consolidate and lithify on a geologic scale. The risk factors would be too high for major construction projects. So there are 5 geologic components to the core of Boston real estate that end with 400 acres of some of the most valuable property in the U.S. First, the bedrock is about 500 million years old and surfaced with the formation of the ancient supercontinent Pangaea and the Appalachian Mountain Belt. Second are the associated basins and basin fill with the split of Africa and North America. Third is the development of glacier and their impact with till. Fourth is the rising sea level that drowned the lower elevation landforms that existed and formed the harbor. And finally was the development and later infilling of the tidal ponds built for tidal mills and the production of flour. Now you understand why there is approximately 400 acres of real estate in downtown Boston with a distinctly different, more intense development style. Value is controlled by geology. Perhaps you have locations that you would like a brief to extended geologic investigation. Please email us at Magnet Geological with your locations and requests. Next, let's have a quick look at Manhattan real estate and geology. Recall from the Boston geology that Africa and North America first collided, then pulled apart, separated. During the collision you get faults parallel to the trend of Manhattan, parallel to the rivers on either side. Some of these are thrust faults. One layer of material is forced over another, it is thrust upon that layer. In this bulldozer analogy, Africa is coming at you, driving material over you, thrusting material over you. Thrusting can, and has imported rock formations from many miles away. Once the compression and thrusting has stopped, then the forces reverse and the environment is said to be tensional instead of compressional. With this relaxed environment, the rock formation begins to settle along the perpendicular fractures that were formed earlier. These form small basins or grabens. If only one fault on one side, perhaps it is a half-graben. This secondary separating trend is called rifting. The primary trend becomes a rifting trend, and the secondary perpendicular faults are likely early transform faults. If we outline the taller buildings in the area, we begin to see both the primary trend and the secondary perpendicular trend. It appears the primary value trend is associated with the secondary geologic trend. Next, we do a little digging and find a depth to bedrock map. That is, how deep is it to the primary rocks and primary trend? It is easily seen from this map that there is a close association between shallow depth and primary building. The shorter buildings are associated with the greater depth to bedrock. This is similar to Boston. If you don't have the ability to safely set your foundation, then you cannot build the taller, more valuable buildings. Now we have a vision and can start building a mental model of the Manhattan subsurface. Imagine Manhattan being pulled apart, ever so slightly, from the north and the south. A break in the rock allows the Manhattan Formation to slide down, like a trapdoor falling open. In this case, hinged on the right and sliding down on the left. The vacancy left behind is filled by new material that is less competent, less strong than the Manhattan Formation. You might think of the East Village and West Village as lying above the trapdoor. The core of how any rock will behave is its chemistry. Mr. Johnson developed some geochemical tools for a quick look at the rocks. This chart is a ratio between aluminum and silicon in the Manhattan Rock Formation. It is compared to approximate ratios from known clay minerals. So very quickly and inexpensively, you can have a look at competency and swelling potential. You need the raw data to do this, which may require some tests, but still very inexpensive in comparison to real estate values and foundation construction costs. Okay, Bud, is there anything you would like to add to the Manhattan conversation?
Thanks, Allison. Good presentation. The west coast of North America, like California, and the west coast of South America are referred to as the leading edges of their respective continents. The east coast, like New York or Brazil, are deemed trailing edges. Active margin and passive margin are frequently used synonyms. This is plate tectonics, of course. Collectively, we are sliding west, overriding the Pacific plates, which are being subducted under our respective plates. Next is an overview of some factors that affect earthquake intensity, and we will use Mexico City as an example. Earthquakes and seismicity are complicated. It can be understood best in three parts. First, by magnitude and distance. How big is the earthquake, and how close are you to it? These two things together can give you a sense of the intensity of the quake. This applies primarily to near-sourced earthquakes, perhaps within 5 to 10 miles of your structure. Second has to do with the local geology, the local terrain, if you will. When the earthquake arrives from a more distant location, are you standing on granite? Or are you standing on something more like a trampoline that can amplify the quake? The informal term for this is the shake in the quake. How much shake is in the quake? Third is an interesting concept. It has to do with the building construction and how that building and ground resonate or act together. Think of a rocking boat, and everyone moves to the same side of the boat. By moving together, they amplify the rocking effect. By resonating, by acting together, they turn the boat over. If the ground and soil under the building and the building resonate or act together, it is more likely to damage the building. If the ground and the building are swaying together, they are more apt to bring the building down. Ironically, fast tends to resonate with slow, and slow tends to resonate with fast. Mexico City has an interesting combination of factors. First, they are a part of the leading edge of North America, and, like the western U.S., they have a dual subduction zone. This means the subducting continent goes down at the west coast, then flat, then down again, and this is just west of Mexico City. This results in oceanic subduction in the middle of Mexico, close to Mexico City. Subduction means there will be earthquakes. Second, Mexico City sits up topographically high, over 7,000 feet. It is like being on a high deck on a cruise ship. And third, it is built on a lake basin. This lake basin is sort of like a trampoline mentioned above. So from time to time during an earthquake, Mexico City is like jumping up and down on a trampoline on the top deck of a cruise ship during a very rough sea storm. It is difficult for buildings to stay upright. Hopefully, that will help with your insight into earthquakes. This is a good time to change topics and introduce you to intrinsic land evaluations. Disaggregation suggests the breakup of a larger accumulated entity into its component parts for evaluation. Consider the accumulation of stocks in a portfolio, then the subsequent disaggregation of the portfolio and the evaluation of each individual stock. That is disaggregation. In contrast, an intrinsic quality of real estate is a component that is a natural part of the real estate and was not accumulated to that real estate. Your shoes are accumulated to your person. Your eye color is an intrinsic quality. In real estate, a petroleum reservoir under the surface is intrinsic to the property. An off-property earthquake-producing fault line is an intrinsic quality to that property, even though it is off-property. A freshwater aquifer and a mineral deposit are both intrinsic qualities. An intrinsic quality in real estate is not or was not originally dependent on human activity, but may be subsequently affected by human activity. Magnet Geological focuses on identifying intrinsic qualities and attempts to quantify them through risk and by means of a discounted net present value. Let's consider petroleum, commercial real estate, and seismicity. Naturally occurring petroleum is a part of real estate. To value an oil and gas well, or a field or pool, there are three primary factors. First, the cumulative oil that will be produced from the well, how much oil can be recovered from the well, field, or pool. Second, the initial producing rate, how fast can it come out? And third, the production rate over the life of the well. This is the monthly income. The first two factors are tied to geology. The cumulative oil is related total pore space or storage space within the reservoir. The initial production rate is related to permeability, or how well the pore space is connected. The lifelong production rate is related to those two factors, porosity and permeability, and also it is related to the well operations, and then converting to income by using the oil price. The value is calculated from the discounting the monthly income to net present value. From your porosity, permeability, operations, and oil price comes your net present value. If you decouple from the price, then you can calculate NPV in barrels. In resource plays or fracking, the cumulative oil is also related to the length of the lateral component of the well to access larger volumes. And the frac, or a larger frac, is related to enhancing the permeability. Both act to add value. The same ideas are used for commercial real estate. In this graph, consider a building that has been constructed. It takes some time to reach full occupancy, then, ignoring appreciation and inflation, it begins its path towards obsolescence. The total value is the cumulative sum of the NOI for the life of the building. However, net present value, or NPV, is typically calculated many times along the life of the building. Perhaps the building changes ownership 10 times over 50 years. There are many discounted values calculated with each transaction. So now think of a geohazard like seismicity. If you were buying a building in Mexico City, did you negotiate a seismic discount? Or did you pay a premium for the design and construction of a new seismic-resistant building? And perhaps for the next 20 years, there is no cost difference. And then comes the earthquake. In this case, you have some sort of an initial investment or savings, then say 20 years of no returns, And finally, the quake happens. Perhaps you paid $1 million extra in the beginning for the seismic resistant design, and that saved $20 million, but it was 20 years later. What is that value? For starters, it is a 16.16% internal rate of return. And assuming you have a 10% discount rate, the net present value of the $1 million investment at the time of the earthquake was $1,973,000. You saved your building and nearly doubled your money. This is also above and beyond what you made on your building from leases. Again, after applying your discount rate, you still doubled your money and saved your building. We can discuss risks later, but in this case, your risk is 100%. There will be another earthquake in Mexico City. The probability factor becomes when will it happen? What is the recurrence factor? Will it happen in 10 years, 100 years, or 1,000 years? The last two major Mexico City earthquakes were in 2017 and 1985. That is 32 years apart. The most current recurrence factor is 32 years. Next, Michael and Allison will walk you through some of our thoughts on agriculture.
Thanks, Bud. Let's begin by considering a Greek philosophical idea. You cannot step into the same river twice. This statement, attributed to Heraclitus, highlights the ever-changing nature of the world. We think of mountains, rocks, and soils as being permanent. They are not. They are as mobile as water down a stream. What is different is the rate of flow. It is a slower rate than your perception naturally understands, and therefore it is typically overlooked. It is fundamental that you begin your understanding of land and real estate with the idea that everything is moving, everything is flowing. To illustrate this, let's examine a cross-section from Google Earth. This section stretches from India, across the towering Himalayan mountains, through Mongolia and eastern Russia, to Alaska. It continues across the northeastern Pacific Ocean, traverses the Rocky Mountains, the Great Plains of the U.S., the Appalachian Mountains, the Piedmont, and finally into the Atlantic Ocean. Now, compare the Himalayas to the Appalachian Mountains, both formed from the collision of continents. Appalachia, in contrast, appears far less imposing than the Himalayas. Why is this? The answer lies in time. The Appalachians formed approximately 250 million years before the Himalayas. This significant head start means they've undergone far more erosion, and, since the onset of Atlantic Ocean rifting, they have changed from being the leading edge of a continent to the trailing edge of the continent. Shifting focus, let's examine the northeastern corner of the Pacific Ocean, between Alaska and the U.S. West Coast. Here, older mixed rock material is eroded from the highlands and carried into the ocean basin. Here it combines with seawater and is subducted back into the Earth's crust and mantle. As it sinks, increasing temperature and pressure cause water to facilitate the melting of the subducted material. This molten material rises, lifting and melting the crust until it surfaces as volcanic lava. Once at the surface, it mingles with freshwater and organic matter, forming soil, which begins its journey back to the ocean. Agriculture lives in this interval between the ocean and the uplifted highlands with its mix of sedimentary, metamorphic, and igneous volcanic rocks. The soil is the foundation of agriculture. Its journey begins in the highlands with the weathering of the parent rocks into smaller portable material where it can be transported into streams. At this point, it alternates between being streambed material and stream deposits. The stream deposits then become the fertile, loamy soils that provide the best agriculture. The original example of this is the Tigris and Euphrates River valleys, whose material originated from the Taurus Mountains that led to the first large coevolution of agriculture and civilization of the Sumerians. Soil formation is, at its core, a mechanism of material conversion for transport downslope by fluvial forces. Minor variations include ice and wind. Glaciers grind rock into till before soil forms, while wind sorts material, blowing fine particles like clay from Saudi Arabia into the Tigris Valley, leaving coarser sand behind. Upon reaching the coast by fluvial systems, soil is first sorted and deposited as beaches or deltaic sequences. Next, it is further transported downslope but under subaqueous conditions, the primary mechanism being turbidites with flanking contourates and ultimately accumulating as seafloor fans, completing its journey from mountain peaks to ocean depths. Returning to the Appalachian Mountains, we could better understand their history. As the continents began rifting apart, the collision that formed the Appalachians ceased. Left without uplift, the mountains eroded into the sea. What remains are their roots, which continue to erode, forming the current topography. Additionally, is the Piedmont, a region of eroded material lying east from these ancient mountains. Piedmont is also a generic geologic term for a flat plain of eroded highland material. This geological journey of the soil echoes Heraclitus's idea, change is the only constant. His insight, that one cannot step into the same river twice, captures the essence of soils migrating downslope. Mountains form, volcanoes erupt, and rocks are converted to soils to be transported into the sea, only to resurface and begin the cycle anew. On a broader scale, the planet spins on its axis daily and orbits the sun yearly. The magnitude of these movements dwarf the gradual processes of mountain formation and erosion. Yet, because mountain changes occur so slowly, we perceive them as being constant. They are not constant. To understand real estate and agriculture, look at what you have. What is upslope and what is your rate of change? Remember, you can never step into the same river twice.
Thanks, Michael. With that foundation, let's turn to intrinsic evaluations of agricultural lands. In the 1990s, Mr. Johnson, drawing from his lifelong ranching and geological background, developed a livestock rotation system for cattle on his west central Texas ranch. His system was rooted in a geologic understanding of the coevolution of bison and grasses, blending ecological science with practical ranch management. To set the stage, let's revisit bison evolution. Over the past 2.5 million years, bison originated in what is now Russia and migrated into North America during Pleistocene glacial events. Once here, they thrived as migratory grazers across the Great Plains, from Canada to Texas. Over millions of years and countless iterations, bison and native grasses developed a mutually sustainable relationship. Mr. Johnson translated this natural geologic history into a system that balanced profitability with sustainability for his ranch. By implementing this coevolutionary rotational grazing method, he maintained the same herd size and gross sales while reducing operating costs by a remarkable 80%. Lower costs translated to reduced inputs, including feed products and fuel. These reductions not only maximized profits, but also minimized environmental impacts, including carbon emissions, while maintaining a sustainable balance on the land. The financial principle behind this success is simple: sustainability as a function of operating efficiency. Specifically, sustainability is calculated as 1 minus the operating expense ratio, OER, expressed as a percentage. For example, if your operating costs are $75 and your gross sales are $100, your OER is 75%, making your sustainability 25%. In this case, 75% of your income is consumed by costs, while only 25% is sustainable. By implementing his rotational grazing system, Mr. Johnson's ranch achieved 90% sustainability. His only significant inputs were free choice molasses tubs with essential vitamins, minerals, and protein for his livestock. What intrinsic qualities of agricultural land contribute to both sustainability and profitability? There are two primary factors: the parent material influencing soil development and the climatic balance of rainfall and evaporation. First, soil quality is crucial. For example, in areas with highly erodible clay formations, soil may never adequately develop, limiting long-term productivity. Without sufficient soil, sustainable operations become challenging. If irrigation is introduced to offset a lack of moisture, costs rise, and sustainability declines. Over time, irrigation depletes water resources and accelerates nutrient loss, requiring further inputs like fertilizers. On the other end of the spectrum, excessive precipitation can leach soils of vital nutrients. These leached soils often require compensatory measures, including fertilizers, pesticides, and herbicides. These inputs increase costs and environmental impacts while demanding additional equipment and labor. The ideal agricultural property strikes a balance. It features natural soil fertility and sufficient moisture to eliminate the need for extensive irrigation or inputs while avoiding the overabundance of water that leads to leaching. Properties in these balanced locations, with moderate rainfall and fertile soil, tend to yield the highest long-term net present value in agriculture. Ultimately, sustainability and profitability hinge on the synergy of natural conditions and effective management. Mr. Johnson's approach exemplifies how understanding the intrinsic qualities of land can lead to excellent outcomes for both the agriculturist and the environment. Now, let's clarify two terms that often cause confusion: regenerative and sustainable. At Magnet Geological, this is how we use these terms. Regenerative refers to the ability to regrow or replace something lost. A starfish, for example, can regenerate a lost arm. However, regeneration alone doesn't guarantee survival. If the starfish is removed from water, it may still regenerate, but it won't be sustainable. It cannot survive in an environment that doesn't meet its needs. In livestock grazing systems, grasses might be regenerative, demonstrating enhanced regrowth after grazing. However, if the system relies on inputs like fertilizers and herbicides, it is not sustainable. These inputs can compromise the operation's long-term viability or, at the very least, lower its sustainability score. In short, a system can be regenerative without being sustainable. Mr. Johnson's approach achieved both. By aligning grazing practices with the natural coevolution of grasses and grazers, he minimized external inputs while promoting the natural regeneration of vegetation. This integration made his system both sustainable and regenerative. Interestingly, there's often a philosophical difference in framing these concepts. In agriculture, practitioners often view regenerative as the overarching concept, emphasizing renewal and restoration. At Magnet Geological, we consider sustainability to be the umbrella term, encompassing regenerative processes, as one subset of a broader, long-term strategy. This distinction is more than semantics. It reflects different ways of thinking about systems. Regeneration focuses on cycles and recovery, while sustainability considers the entire system's capacity to endure without depleting its foundational resources. Both are essential, but their roles and priorities vary depending on perspective. At Magnet Geological, sustainability is the ultimate objective. To support sustainability goals, Magnet Geological offers a comprehensive soil testing and interpretation service. This includes full agricultural tests alongside complete elemental analyses, such as rare earth elements, precious metals, and minerals like quartz and clay speciation. It's important to clarify that, in this context, mineral testing refers to geological components rather than oil and gas. Those are covered by a different section. These tests encompass everything in geology and geochemistry, but do not include geotechnical engineering evaluations. If you're planning a large construction project on your real estate, you will ultimately need the expertise of a geotechnical engineering firm. Next, Michael will return to discuss mining mineralogy and petroleum.
Thanks, Allison. As she started showing you, Magnet Geological provides a full testing and interpretation services as needed. Our geochemical test typically includes a range of analysis to fully evaluate your resource from agriculture to rare earth elements and precious metals. Mining in the United States is large, about 12,000 mines and quarries. Today we are just going to talk a bit about rare earth elements, enhanced weathering, and aggregate quarries in Texas. Rare earth elements are not particularly rare and can be found anywhere. The ultimate origin is in the mantle where they surface through igneous rocks. There is a tendency for them to be associated with rock types such as carbonatites, pegmatites, and peralkaline granites. The mineralogy includes monazite, xenotime, allanite, eudelite, bastnasite, zircon, perithalite, and nitrofluorite. These elements, while they originally start in mantle rocks, can also be weathered out of the rocks and be found in their mineral form in placer deposits and third weather out of the minerals to become ionized elements and react with clay or other minerals in a sedimentary environment. Texas has 3 in-state, non-sedimentary environments where rare earth elements might originate, and they include the Ouachita Front, Llano Uplift, and the West Texas igneous terrain, including the basin and range to Rio Grande Rift areas. Round Top Mountain, owned by the state of Texas, is the most notable known accumulation in the state, and it is a first-order accumulation in a peralkaline rhyolite. From these three sources and the Rocky Mountain out-of-state sources, rare earth elements could be located anywhere in the state, more generally, anywhere in the world. We are continually surprised with all the places they turn up. We encourage you to test for them. Enhanced weathering is an interesting geochemical idea. Worldwide basalt rocks react with atmospheric carbon to form calcite and dolomite. Essentially, carbon dioxide becomes carbonic acid, which reacts with the silicate minerals that converts the carbonic acid to calcium carbonate. The idea of enhanced weathering is to hurry this process along by administering basalt rocks to more humid environments for enhanced weathering. The interesting part is looking for the right rocks, such that the byproducts of the process are also an enhancement to the original soil. If these are applied to a high silica-based leached soil, a clay-type byproduct such as kaolinite or smectite could provide a higher CEC to the leached soil, which would reduce the operating costs and further enhance sustainability. Mr. Johnson spent a lot of time looking at the conversion from fresh volcanic basalt to vegetative areas in Sicily, particularly at Mount Etna and Stromboli in the Aeolian Islands. The richness of the soils is unmistakable, and he encourages everyone to look into this opportunity. Finally, aggregate is used universally from road base to road material to concrete and masonry sand. It is used as railroad ballast to bunker sand, filtration media to frac sand. The question always is, what else is with it? This is a standard geochemical test for us. We encourage the testing of all sedimentary detrital formations. Regarding petroleum, Mr. Johnson discovered two oil fields in the 1990s. One is an infinite water drive reservoir without reservoir pressure depletion. It is a carbonate with secondary porosity enhancement by subaerial exposure and leaching. The other is a solution gas drive pressure depletion reservoir. It was formed as a detrital tabulata coral with excellent porosity and permeability. After 2005, Mr. Johnson was involved in over 2,000 wells as a consultant in the eastern shelf of the Permian Basin. Along with petroleum is carbon sequestration in saline reservoirs. In short, this is capturing CO2 and pumping it down to critical depth such that it is a liquid and is available to re-inject into a saline reservoir for permanent sequestration. Mr. Johnson has completed a study on a large 77,000-acre CO2 sequestration project in Texas. Magnet Geological is happy to assist with a wide variety of issues, from exploration projects to 1031 exchanges in and out of the petroleum industry. Don't hesitate to email us regarding any petroleum or mining questions. Next, Allison will cover some freshwater and geohazard issues.
Thanks, Mike. Early in this video, Bud mentioned the idea of walking the halls of the Louvre with the paintings facing the walls. In geology, it is as important to see the risks as the opportunities. We discussed seismic-related events earlier, but other geohazards can also pose risks. It is said that expansive clays are the #1 cause of structural damage in the U.S. A soil with expansive clays typically looks healthy and inviting. Historically, homebuilders just laid the foundation down on top of the expansive clays. Years down the road, there is doming and dishing under the house, and deciding which side of the house got more water or more sunshine. From an investment standpoint, it is best just to stay away from these if possible, and if not, substitute a non-swelling base material for the expansive clays, or at least mix it with a mitigating material. Use your geotechnical engineers, of course, but it might not hurt to have your A, B, and C horizons fully geochemically tested by Magnet Geological prior to purchase. Then you know what you are getting into. Landslides and debris flows are generally related to a change in pore pressure on a slope. The increased pore pressure comes from added water in a particular horizon, which reduces the friction between the overlying and underlying horizons. With this, the overlying horizon slides over the underlying interval either quickly or in a slow creep fashion. Be aware of multiple shear zones and stay away if possible. These can be very difficult to stabilize. Liquefaction and dissolution cavities like sinkholes and casting swallow your structure. In north-central Texas, there is a drilling rig that sank about 70 feet straight down during drilling. This was related to dissolution of salts and gypsum combined with liquefaction. In general, dissolution of evaporites like that of Texas and found in other areas of the country with salt deposits, is generally second to casting, which is the worst in Florida, but can occur anywhere including central Texas, Kentucky and Minnesota. Again, best is to stay away if possible. If not, watch for the dissolution trends. They can be dendritic, but generally they are along a fracture pattern. They tend to be exacerbated by property development. The Pleistocene period was a wetter period for Texas and many western states in the U.S. than is the case today. As a result, streams are said to be underfit, that is, they have less water in them than what appears to fit the valley. As this is not well known or recognized, many structures are built on what would have been the Pleistocene streambed, thinking it is a floodplain. The first known flooded structure in Texas was in San Antonio in 1724. It was the Mission San Antonio de Valero, and founded 6 years earlier in 1718. After the 1724 flood, the mission was moved out of the flood plain to a slightly higher location, and still stands to this day, and is known as the Alamo. Besides the Pleistocene streambed, there are 4 additional flood factors that are easy to ascertain. First, in a steep slope stream, there will be high velocities with point bars and cut banks. Be especially aware of the cut banks and the forward development of the cut banks. Second, watch for slope decreases, and usually with a coalescence of streams. This is typically the worst flooded areas. They are flat and easy to build on. Near stream locations have high velocity and high water levels. Away from the streams are high water levels and slow velocities. Third is land subsidence. Ground subsidence is real. There are 2 factors. As fluids are removed, buoyancy is reduced. If you pump water out of a reservoir, the grains consolidate. But more importantly, as material is brought into a coastal environment, the subsurface compensates for the added material, it sinks. The ground naturally sinks. The Texas coast has over 5,000 feet of relatively recent subsidence. Fourth is development. Unintuitively, this is heavily affected by climate. Soil has a certain moisture holding capacity. It is in the range of 1.25 gallons per square foot for 1 foot soil depth. In a drier climate, the soil moisture can dry out, evaporate, and then catch another 1.25 gallons. Texas tends to have 2 wet seasons, spring and fall, hence this is a very reasonable assumption for central Texas. 5,000 square feet in a single lot of covered soil in 2 wet periods contributes an extra 12,500 gallons of runoff. That is about 10% of the annual house usage. Things change as we move east and southeast. It rains much more, so a soil has less chance to dry out. As a consequence, it will likely be much more saturated. When it rains, if that new water hits a roof or a saturated soil, it will run off either way. So, wet climates tend to mitigate property development flood issues. Soil types are also a factor, but for another discussion. Recapping: flooding, Pleistocene streambeds, steep stream slope issues, coalescing streams with decreasing slopes, land subsidence, and added property development. So really, since the Alamo flood in 1724, there is no real reason to have a flooded property in Texas except by choice. There are many software packages and flood specialty groups, but from an investment standpoint, it is very elementary to stay out of flood issues, if that is your choice and desire. Most geohazards have their predictable characteristics, including wildfires. If Magnet Geological can be of assistance with your investment or finance decisions regarding any of these issues, please let us know. Next, we can have a quick look at freshwater reservoirs or aquifers. Generally, an aquifer is a shortcut from the fluvial system for the water traveling between mountains and oceans. There are exceptions, but that is the easiest way to envision the aquifer. The key elements are the recharge area and the discharge area, which is generally a spring at the surface downslope. The fluid volume in the reservoir is the formation volume times the pore space in the formation. How the fluid travels in the reservoir is related to the slope of the reservoir and the permeability is how well the pore spaces are connected. For a producing well in an aquifer, it is important to remember that water is lost at both the discharge location and from the producing well, not just the well. A key ratio for magnet geological is the ratio of well head over the discharge head. This ratio yields a sense of proportion of the aquifer that your well is producing from. And in turn, you can arrive at a sense of value. For example, you might be producing from 75% of the aquifer, or maybe you only have access to 25%. How does your well compare to other wells in the aquifer? With very little information, we can get a quick evaluation of the aquifer. This chart represents the values that could be used for an NPV calculation. From this you can work towards actual water volumes and values per unit of water. Perhaps you are selling the water, or perhaps you are estimating the cost of the water for another use. What is the cost of installing the well versus the gains from the well? Another important factor in an aquifer is the type of reservoir, the type of material that makes up the reservoir. As mentioned before, an aquifer is essentially a shortcut downslope. If there is a way, water will search for the shortest path downslope. As a result, we find freshwater in many formations, but the quality varies immensely. In the upper left corner we have sands. The best one has some cement to keep the grains intact, but not enough to significantly hinder the porosity and permeability. The one to the side is unconsolidated, which has better porosity and permeability, but because it is unconsolidated it also moves abundant sand which abrades and deteriorates the pump and equipment. Further down we have limestone, marble and sabkha dissolution aquifers. A sabkha environment is an evaporitic environment. The reservoirs associated with them tend to also have dissolved gypsum and other evaporites. This group is followed in general by more crystalline aquifers such as fractured granites and other igneous and metamorphic rocks. Associated with these are saprolites, which is the weathered crystalline rocks. Saprolites can add porosity, but the clays associated with them can also reduce permeability. At any well or pump, we encourage you to get standing water depth, reservoir depth and a water sample to be thoroughly tested.
Thanks, Allison. A quick note about geothermal. The efficiency of geothermal is tied to the difference in temperature. Iceland has a temperate climate, about 40 Fahrenheit year-round, and it has 2,000-degree magma at the surface. The spread is what makes it work so well there. Without the spread, you lose efficiency and the economics will decrease also. I often hear talk of Texas geothermal, but surface temperatures are hot and geothermal is warm at best, a minimal spread. There is also the use of shallow geothermal. This is a heat pump system using the consistent temperatures of the shallow subsurface, generally numerous holes in the top 400 feet. These systems work, but they are offsetting heating for pumping. Make sure you have a good geothermal engineer to incorporate all of the factors. When you say real estate, you often think of the surface. For a geologist, it might be that the subsurface is the first vision, and then the surface view is a consequence of the subsurface. That is, it's not possible to understand the surface without first understanding the subsurface. This is a manufactured cross-section or profile view and is generally set around central Texas. First is a deep saline aquifer with a potential use for carbon sequestration. Next is an igneous intrusion, numerous along the Balcony's fault zone. Then think of geothermal potentials. As the igneous erodes, there are potential detrital igneous materials deposited on the flanks of the volcano or intrusion. Going deep again, there is the potential for petroleum. Above the petroleum is a potential aquifer, but the recharge zone is in the igneous detrital. How will that affect the water? Above that aquifer is another aquifer with a better recharge source. Near the stream is a sponge aquifer. The river and shallow sponge aquifer readily exchange constituents. Then the river with its issues, like flooding. Next to that is the potential for a gravel quarry. When the volcano went off on the right side, it deposited ash on the left side, which converted to an expanding clay. The developer started a new project on the hill overlooking the valley. Not only did he have swelling soils, but then ran into karsting. And below that, the development allowed more water into the karsting limestone, which subsequently leaked out along the fault plane, contributing to landslides downslope. The water then pooled at the bottom to contribute to liquefaction issues. The liquefaction eliminated the use of the location for a commercial building site. And to complicate matters more, there is a secondary source of water from a paleodeltaic sequence. Further, it is made worse by a new city ordinance mandating the restriction of runoff at the top of the hill. They are now forcing the water into the deltaic system, contributing to landslides, liquefaction, and earthquake generation. Just a few ideas connecting geology and real estate. Thank you for taking the time to follow the presentation. If we can be of assistance, please let us know via email.